Hey everyone, welcome to the first lecture for our very last unit of the semester, where we're going to cover a bunch of different things. So we're going to start off with the functional group called alcohols, and we'll move into some different functional groups throughout the rest of the unit. But to start off with alcohols, you may already be familiar with alcohols because we've seen them in some of our examples so far. But to give it a thorough definition, an alcohol is any kind of carbon chain with an OH group somewhere on it. So we have some examples of this that you've definitely already seen so far. If you've seen CH3OH, that's an alcohol. It's a very small alcohol. You've also probably seen this one, where now we have a couple of carbons. These are just two different ways to write similar alcohols. This one only has one carbon, but this one does have two. So make sure you're counting your carbons. There's this one, which we may have seen so far this semester. We may not have, but you also could easily have used it a lot this semester. This is isopropanol. So if you've seen that, in drugstores before, you've used it to clean wounds. It's also a component of hand sanitizer, as is this one sometimes, which is ethanol. Another one is this. So there's our benzene ring, and we're going to learn a little bit more about benzene later this unit. That is also an alcohol. It looks a little bit different because of that benzene ring. But this is phenol, which that's a slightly different name. You won't need to know any of these names necessarily, but phenol has a very particular smell to it. It's kind of like a Vicks smell. It's got that sort of it's a little bit hard to describe, but it kind of reminds me of like cough syrup, kind of a medicinal smell. And one other alcohol that I think that we can all agree is pretty cool. Let me move this over a little bit. Does that alcohol look familiar to you? It might not, because there's kind of a lot going on there. And there's actually many, many alcohols on here, right? Any of these groups with the OH, that's an alcohol, that's an alcohol. So there's a bunch of alcohols on here. What the heck is this molecule? Well, this is our good friend glucose. So glucose is made up of a bunch of alcohols, and so are all simple sugars. So just really quickly, nomenclature refresher. You will not be asked any nomenclature questions on this exam. I just want to give this little refresher in case you hear me referring to compounds by name. That way you hopefully will be a little bit less lost if I'm just name dropping a bunch of alcohols. So you take your base chain name, whatever that is, the number of carbons that you have, you add an AN, so it'll kind of be like almost the alkane name, but not quite. And then you add an OL suffix, and that stands for alcohol, right? So our examples there. So here's our one carbon alcohol is meth plus AN, and then OL. So methanol is this one here, right? Our one carbon chain. If we look at our two carbon chain, that will be ETH for F is our prefix. AN added on to the end. So that's almost ethane, right? If we just added an E, it would be ethane. But we're not going to add an E, we're going to add an OL for ethanol. So again, you will not be asked any nomenclature questions, just to help you keep up with me speaking a bunch of chemical names at you. So what we're going to talk about mostly today are just alcohols and the reactions thereof. So by the end, it might seem like, oh man, we talked about a bunch of reactions, but I want to highlight for you that we've actually seen most of these already, right? So this is one that you have literally already seen, you have been tested on at this point. This is the reaction of an alkene with H2O and a little bit of acid in there to help kind of speed up the reaction. So this one is called hydration of alkenes. I think that's a pretty logical name, right? Because you are taking water and you're putting it onto an alkene. So an alkene is getting hydrated, hydration of alkenes. So that's the name of this reaction. I'm just going to give you some names so we can kind of help keep track of all the different reactions of alcohols. So we've seen this one before, but let's go through the mechanism again together really quickly. First things first, we have our alkene, and it's not really a good electrophile or a great nucleophile on its own, so we need to do something to help it out with that. And that means we're going to take our acid and protonate it. So reversibly, we can have this. So I'm just abbreviating H2SO4. You could use H3O plus here. Pick your favorite choice of acid. As long as it is a true acid, I will be fine with it. We're going to use the electrons in our alkene. They are going to reach out and pick up that proton. Don't forget we have to break that OH bond, so we need our second arrow right like that. And then we're going to put that hydrogen on one spot or the other, and we want to choose to do this so that we get our most substituted carbocation. So the hydrogen ends up there, and the carbocation ends up there. Next, water can come in. And now that we have a really good, strong electrophile here, water as a weak nucleophile, it's like, okay, you know what? I can get in there now, no problem. Going to attack that carbocation, and we will get this structure here, where there's our H that we just added, and we just added water, like so. Check your charge balance here to make sure that we have a positive charge at this step. We haven't changed anything, we just added two things together, so we must have a positive charge at that step. And then we're almost done, but oxygen doesn't like to be positively charged like that. So we will instead do one last step to pull that off. You can use another molecule of water. You can use the conjugate base of sulfuric acid too. Either one of those is good. We'll pick off one or the other of these protons. Don't forget that second arrow to break our OH bond. And we get to our final product that looks like this. There we go. So this is, again, just a refresher of the things that you've already learned. You already know one reaction of how to make alcohols. You know more than that, but we'll see those coming up in a moment. And so I just want to highlight one point here is that I've drawn these reversible arrows here for all of these steps. And there's an important reason for that, because it'll help you learn this reaction that you actually already know. You didn't even know you knew, but you already know how to turn alcohols back into alkenes. Wow. So this is a kind of a freebie reaction that you already know. And how do you know it? Because it's just the backwards direction of this reaction, the hydration of alkenes. If we go in the backwards direction, all we're doing is dehydrating an alcohol, and that makes an alkene. So this is our second reaction type for the day, is just the backwards reaction of what we've already talked about. So if you take now an alcohol in the presence of just acid, right? So we don't have any extra water in here, and heat, which we know from last unit, helps us favor an E1 style elimination. That's really all we're doing here is an E1 style elimination. So if we go ahead and just do all of the steps in reverse here, we started out with the alcohol, and the last thing we did up above was to take a proton off. So we're going to put one on now. So here's sulfuric acid to act as a proton source. We're going to take the lone pair electrons on oxygen and use those to pick up our proton. Don't forget to break that bond and push our second arrow there. And then we get to that, which is basically now just water that's sort of been added onto that carbon chain. And so what we had in the previous reaction was water attacking a carbocation. Now what we're going to do is have water leave and make a carbocation. So what we'll do is just take these two electrons here in that bond. Water is going to take them away, and we'll make a carbocation. That looks a little something like this. And we will have made some water and ejected it out. You don't have to draw it like this if you don't want to, but that was sort of kind of like a leaving group actually. So the water kind of left and made a carbocation. Now, all we have to do is basically remove a proton and we will be able to get to the alkene. So this is sort of our E1 style step here, right? But you have to be careful when we're thinking about E1 and any elimination. To be fair, we want to be thinking about the regiochemistry. For this example, you already know which product it is we're trying to go to because it's drawn out for you right there. But you do have two options. Let's draw those in. You have a beta position here and there, and they're not identical, so you should consider both of them. But since we know which one we're going to choose this beta position and not the other one. So I'm going to get rid of these annotations and draw in that beta hydrogen. That's the one we're going to remove because there is only one in the product and there are two here. That's another way that you can help check yourself. So we use the water molecule to take off one of these protons. I'm going to move this one just so that it's out of our way. Going to pick up that atom, and then don't forget we have to break this bond. This CH bond breaks and what is allowing us to form our alkene. And then we get to our final product. our alkene. So depending on what it is you want to do, if you have an alkene and you want an alcohol, good, use this reaction. If you have an alcohol and you want an alkene, you are basically using the same reaction. The conditions are slightly different, but the mechanism works exactly the same way, just in reverse. So feel free to practice through some mechanisms of other questions on this one and convince yourself that they are literally all the same steps, just in the backwards order. Nothing tricky here. So it's a freebie, like I said, one that you didn't even know that you already knew. Now let's look at another one that you have already seen before. So this is another one from last unit. We have some kind of chloride leaving group. We treat that with NaOH, and then we end up with an alcohol at the end. And so this is going to happen by a substitution reaction. Pause the video and answer the video question. What type of substitution reaction is happening here? SN1 or SN2? Hopefully you're feeling pretty comfortable with those substitution reactions by now to be able to tell that this is an SN2 substitution because we have OH with a negative charge on it. That is a strong nucleophile. So this is a reaction to form an alcohol via an SN2 substitution. So let's briefly look at the mechanism for this one as well, just to refresh ourselves. We start with a chloride, and then we have Na+, which doesn't do anything, and the OH-, which is our nucleophile. That is what's going to come in and all in one step attack at our electrophilic carbon that's attached to the leaving group and kick the leaving group out like so. And then all in one fell swoop, we get to our product. There you go. Not too bad. So there we go. Again, this one is hopefully not too bad. We've seen it before. But what if, I mean, this worked just a minute ago, right? What if we wanted to go backwards? So we just did this, right? We took the chloride and then we substituted, and we went to the alcohol. But can we do the backwards reaction like we did before? If we had the alcohol, can we go back to the chloride? Is that allowed? Well, the answer is no, not really. And why is that? Well, that's because OH- is a poor leaving group. So if it's a poor leaving group, that means it's not going to be one, right? So I just wanted to compare some of these potential leaving groups to think about the ones that we know here are our good leaving groups. We determined that based on their conjugate acids, pKa. So if we think about HI and HBr, so just looking at the conjugate acids of all of these, we can use their pKa values to tell us a little something about how stable their conjugate bases are. So the pKa value for HI is -11. That means it's a really, really strong acid, which means that I- by itself is happy, it's stable, it doesn't mind giving up that proton. We look at HBr, we're at -9, and HCl is -7, so not too bad. Those are definitely very strong acids still. And HF, despite maybe being sort of seen as a really scary strong acid, it's strong, but not for all the same reasons. That pKa is only 3, and we said that this one is not a leaving group. So fluoride is just not a leaving group, right? We talked about this and looked at it in some of our example problems. When you were given fluorine and bromine at the same time, the fluorine is not the leaving group, the bromine is. So if we think about the pKa value of H2O, which is the conjugate acid of OH-, that value is 15. So it is way, way higher than all the rest of these conjugate acids. And so that means that this is definitely not a leaving group. So if we look at this scale kind of as we go along here, if we draw an arrow in this direction, we know that we're increasing the strength of the conjugate base, which means we're decreasing its stability. So these are stronger bases going in this direction. But that means that we're decreasing leaving group ability. So I guess we can't really do this reaction backwards. Well, you can make this reaction happen, but it's not backwards. It's not the opposite of the SN2 reaction that we use to make the alcohol in the first place. We're going to have to do it by a different method. So what the heck is that method? How will we know what to do? Well, what we need to do is have that OH be a leaving group, but it doesn't do it by itself. So we need to turn it into a better leaving group. And so in order to do that, what we're going to do is protonate it. Why do we need to protonate it? If we compare these two options, let's think about what the leaving group is in either case. In this case, if we're just taking this alcohol and we want to get rid of this, the leaving group would be OH with a negative charge, right? Because remember that every time a leaving group is leaving, it has to take those 2 electrons with it. Same is true over here. But in this case, that's got that extra proton on it. So the Lg in this situation is H2O, right? So if we compare these strengths, OH minus is a strong base. We know this from Gen Chem. But water is a weak base. It's a weak base, it's a weak nucleophile. We learned about that last unit. So that's why we would much prefer to use water or a protonated alcohol as a leaving group, because it's going to leave as a weak base. And the other thing that's nice about this is when we break this bond right here, we get to neutralize the charge on that oxygen to make water, right, with no charge on it whatsoever. And that's nice because oxygen doesn't really like to be positively charged. So if we can make it neutral, it gets really happy. So that's the reason that we want to protonate and use our H2O as a leaving group instead of OH minus. OH minus is never a leaving group. So here's how we can actually do this reaction, is we need some proton source to protonate our alcohol, and then basically the other piece of that needs to be the bit that we want to put on there, right? So in this case, it's going to be a chloride. This also works with HBr. You'd use HBr if you wanted to put a bromine on your molecule instead. So this is a reaction that we will call halide substitution or halide substitution, because we're going to substitute an OH group for a halide. And there's a couple of different ways that this can happen, so we need to look at 2 different mechanisms. If we have a primary or a secondary alcohol, we're going to still do the same step first where we protonate. We'll use the lone pairs on oxygen to pick up the proton from HCl. Don't forget to break that second bond because the chloride is kind of, again, acting like a leaving group here and allowing itself to leave with that set of electrons. Then once you've protonated your alcohol, it has now basically achieved that good leaving group status. And because we have that good leaving group and we, in this case of this reaction, are at a primary center, it's not very crowded. So what we're allowed to do is use that chloride with the minus charge that we made here with that second arrow. That chloride is allowed to come in straight away, attack at this carbon here, which is our alpha carbon right next to that leaving group, and kick the OH2 straight out. And so this is an SN2 step to just get rid of that and substitute it directly for the chlorine, like so. But now if we were to have a tertiary alcohol, it works a little bit differently. First step is still the same, that we have a protonation step where we take our HCl. We use the lone pair of electrons on oxygen to pick up that proton. Again, not forgetting to draw that second arrow, break our HCl bond. And we get to a very similar looking place, but now because this is a tertiary center, that leaving group is pretty good and the tertiary carbon is pretty crowded. So we can't get in there to do SN2. We're never allowed to do SN2 on tertiary centers. So what's going to happen instead is this will happen more SN1-like, that our leaving group is going to leave on its own first. We get a carbocation. You are going to be absolutely sure to check for rearrangements here and rearrange if necessary. For this one, there's no rearrangements that would give us any more stability, so we're going to stay right here. And then our chloride can come in, and now that that leaving group is gone and we have this highly reactive carbocation, it can come in and attack there to form a new bond to make our chloride. So this reaction is very similar depending on which substrate you have, but the mechanisms are slightly different in that if we have a less hindered substrate, it acts like an SN2 reaction, and if it's more hindered or tertiary, then we're doing this basically by an SN1 mechanism. So with that, we've talked about a few reactions so far. Let's take a little PTP break and do a little practice. Let's do some predict the products questions. So for this first one, I didn't tell you what type of reactions we're doing here, so everything we've learned so far is fair game. We have to analyze a little bit and see what it seems like is possible to do here. So we're starting out with an alcohol. If that's the case, then we're probably talking about something from this lecture and from this unit. So we are treating it with H2SO4, and here's our little hint. With the temperature, that means that we're giving this a lot of heat, and we know heat favors elimination. So I would say here that we are going to be dehydrating this alcohol to make an alkene. And we know that we did that by an E1 sort of like mechanism. So feel free to draw through the mechanism to help you predict the product if that's what you like to do. I'm going to skip a little bit of that, however, and just draw out this carbocation because I know that's where our leaving group is going to leave from after we protonate it. So we're going to get that carbocation. Ask yourself, are there any rearrangements that we need to do here? And if so, we better do them. To me, it looks like we have a tertiary carbon right over here adjacent to our positive charge. So we definitely want to rearrange. Let's take the one hydrogen that's here, use it and its 2 electrons to scoot over onto that positive charge. And then that will get us to that carbocation. So now that we have that carbocation, the last thing that we're doing is just doing our elimination here. So we have to think about where our beta positions are. Beta, beta, and beta. There's 3 of them, but are any of them identical? Yes, these 2 kind of out to either side are identical. So we're just going to go ahead and ignore one of them and think about the other. So we have one out here toward the bottom that is a primary beta position, and this one is secondary. So we want to favor the most substituted beta position so that we can get the most substituted alkene. So that position is out. We want to be thinking about that position there. So we want to draw an alkene between those 2 carbons. So our final product will look something like this, where we've now made a new alkene between sort of that carbon where our leaving group left from originally and that center position with the methyl group on it. So again, this is an example of one where we did a rearrangement and maybe it didn't actually matter in the general scope of the reaction, that you might have guessed this product even without doing the rearrangement, but you should always do the rearrangement just to be sure you don't miss something. So I'm going to go ahead and rearrange this a little bit for the sake of the design of the slide. And now we can move on and try this next one, shall we? So here we have a Br, so that definitely looks like our leaving group here. And then we're treating that with NaOH. So having a good leaving group in place, and then we've got some kind of a base or nucleophile over our arrow, that makes me think we're doing substitution or elimination. So let's just go in and analyze like we always do for those types of reactions. At our leaving group's carbon, we have a secondary substitution. And then we want to think about our nucleophile slash base. We have a positively charged cation, and then we have a negatively charged OH group. So this is a strong nucleophile or a base. But when it comes to base and nucleophilic ability, since this is pretty small, we can go ahead and assume that it will act as a nucleophile. And so that would be putting us in the SN2 category here. So nothing is going to happen to this cyclohexane ring. It's all going to stay there. Nothing's going to happen to those 2 carbons hanging out, but we are going to have our OH minus come in as our nucleophile. And because I gave you some stereochemistry here, you probably want to be careful about your stereochemistry in the product, that this has to come in from the back side or behind the leaving group. So our OH is going to come in as a dash. Let's do one more. Here we're taking an alcohol and treating that with HBr. Go ahead and pause the video here to make a quick prediction. Hopefully this one looks familiar from what we were just talking about. If we're starting with an alcohol, like I said, that's probably going to be something from this lecture and this unit. So we want to think about what can we do with that alcohol? Well, we have a strong acid here, and instead of it being H2SO4, there's no heat. We're not making an alkene, right? We're not doing an elimination. We're going to be doing a substitution here. So we're going to protonate this OH with the acid part of HBr, and then the Br can come in as our nucleophile and basically just substitute for it directly. We can think about the type of mechanism that that would go through, because this is a primary alcohol or a primary leaving group, right? So that means that this is going to happen by an SN2 style mechanism, and so we don't have to worry about any carbocations or rearrangements. So our product will look something like this, where the Br comes in exactly where that OH was. And if you're not sure with any of these, please be sure to double check your carbon count and think about, be really careful with thinking about rearrangements, just so that you're always kind of heading down the right reaction pathway. Okay, let's go back to a couple more newer reactions. So this is a new version of something that you do already know. So this is a reaction called the Williamson ether synthesis. Why is it called the Williamson ether synthesis? Because some old, currently dead guy named Williamson came up with it. So this particular piece right here is what we call an ether. That's any single bonded oxygen between basically two carbons, right? So if we have that single bonded between these two carbon groups, then that's an ether. You can have symmetric ethers, you can have unsymmetric ethers, you can have cyclic ethers. We'll see some examples of those in a moment. So we are basically making an ether from an alcohol that we started with. And there's two steps to this reaction, which means that you add the first thing and you wait a little bit, you let that do what it's going to do. And then later you add the second thing in. That's all that means. We're just doing them in a specific order, and the order does matter. So first we use this NaH. What the heck is NaH? What does that even do? Go ahead and use your reaction, your substitution elimination reaction analysis here, that we know sodium always has a positive charge. So what charge is on this hydrogen? It has to be a negative charge. So this is kind of weird, right? Hydrogen has always been positively charged, like for as long as you've been in chemistry. But sometimes it can have a negative charge. And when it has a negative charge, we call that a hydride. When it's a positive charge, we call it a proton. If it's a negative charge, it's called a hydride. And so sodium hydride is what we have as our first step here, and that is going to act as a base. We'll see this happen in the mechanism in a minute. Then we add in this piece here that I've just given some generic carbon chain with an Lg on it. It can be any Lg, it doesn't really matter. So what exactly are we doing here? Let's take a look at this in the mechanism to get more of the details. So when we're drawing through the mechanism, we want to start with our first step first. So we have our Na plus and our H minus. You can even draw in a pair of electrons on that hydrogen, even though it looks kind of weird, at least it does to me. That hydrogen has a pair of electrons to it. And so what this is going to do is act as a base, and that means it's going to pick off the most acidic proton on our molecule here. But which one is the most acidic proton? It is by far and away going to be the OH proton, pKa of about 15, right? Any of these other CH protons are much higher in pKa value. That means they're weak acids. So this H minus is going to pick off that H. And don't forget, we always have to, if we're taking off a proton like this, we have to break that other bond and set those electrons over on the oxygen in this case. So we end up with this. And what byproduct did we just make? We used an H to pick up another H. So what we've done here is make H2 gas. And why is that cool? Well, partly because hydrogen gas is just kind of cool, but it's cool because it's a gas. And that means that it will just sort of bubble out our solution and it will go away. if you look back on the previous slides where we did some acid-base chemistry, I normally draw that as a reversible set of arrows, meaning that it can kind of go backwards and forwards and there's an equilibrium. There is no equilibrium here because hydrogen gas is formed, it bubbles out of your flask and it goes out into the universe and it does not go reversibly backwards. So that's cool. That's our step one. We used up the NaH and we have this thing. Cool. So what is that? What does that do for us? Well, it's maybe a little bit hard to tell out of context, but if we bring in the piece from step 2 that looks like this, now we can kind of think about these two things together. We have a leaving group here on a primary carbon. We have this thing, right, which has a negative charge on it, and it's not terribly branchy or crowded. So this piece over here is our electrophile that we're just adding in step 2. And essentially what we did in step 1 is we made ourselves a good, strong nucleophile, right? We just did a little bit of acid base. We created this O with a negative charge on it. So now we have this strong nucleophile. We have a non-crowded substrate or electrophile. So what we're going to do is just a little bit of SN2. So we're going to take one of the lone pairs or this negative charge from the O minus, attack at our alpha carbon that has the leaving group on it, kick the leaving group out, and we will achieve our product, just like so. So really this is all we're doing is just doing an acid base step first and then doing an SN2 reaction. So this is just an SN2 that you had to do a little bit of work before you could do the SN2. So basically it's something you already know because you definitely know acid-base chemistry and you definitely know SN2 chemistry. So there you have it. It's just kind of combining those two together. So one quick last note here is that you can do this with any carbon chain, right, for your alcohol piece here, as long as it is primary or secondary. If it gets to be tertiary, then it's going to be a little bit too crowded and this won't work well, and it will maybe do some other reactions that we don't want to do. If you want to make an ether, it probably needs to be primary or secondary. Okay, so here's another one, kind of a special example of that ether synthesis. This is maybe a little bit of a weird one. So take a second, pause the video here and think about it for a moment. If I take this substrate here and I just treat that with NaH, so now there's no two steps, we just NaH, that's it. Pause the video and predict what you think the product of this reaction might be. If you feel like you have no clue, let's look through the mechanism quickly to maybe help get us an idea. So we're going to start off with our NaH just like we did before. You don't have to even draw in this sodium if you don't want to. You can just draw in the hydrogen if you like. And by hydrogen, I mean hydride specifically. So we know that wants to react with an acidic proton. Our OH proton is still the most acidic one here. So we're going to pick that one off just like we did on the previous slide. Like so. We get to this O with a negative charge on it. And now what? Like I said, there's no second step. We aren't adding in an electrophile. But if you think about it, we do have a leaving group right here. So that means that this carbon that's attached to that bromine is actually kind of electrophilic. So what we have happen here is maybe a little bit odd, but we use the oxygen with the negative charge to attack right there at the carbon with the bromine and kick the bromine out. And that makes us this slightly unusual product, where we didn't do anything, we kept the bond from the oxygen to that carbon, but we also made a new bond with the oxygen to that purple dot carbon. So that's a little strange, isn't it? Yeah, and for more than one reason. We made this kind of tiny little ring. If you turn it on its side, actually, looks like a little party hat on our cyclohexane ring there. But the other thing that was weird about that is that it happened, the molecule sort of turned on itself, right? And this is something that you may not have heard before, but this is a common thing that will happen in organic chemistry, is an intra molecular reaction. And so when I say intra, that means, like within itself. That means a compound is going to react with or on itself. So this one can be a little bit tricky, especially with spelling, but intra means within. If you see inter, molecular reaction, that means that it's between two molecules. But we normally just sort of assume that that's the standard for chemistry. So we don't normally say that. We usually just specify if it's happening on itself, we say intra. So now you know about intramolecular reactions. But other than that, why is this cool? Why do we even care? So this is a special example because of this kind of weird party hat ring, right? This three-membered ring where we have the oxygen is one piece and then has two carbons and they're all connected together. And so when we make a molecule with this sort of functional group to it, we call it the name of epoxide. And maybe epoxide sounds a little bit similar to something that you've heard before. It sounds familiar to you, perhaps. And that's because it forms the basis of epoxy. If you've ever done any sort of DIY or building, you may have used epoxy resin, epoxy glue. And so epoxy is just a polymer. Yay, polymers, they're coming back. So it's a polymer that's made from epoxides. Hence the name epoxy. So if you've used this before, then you probably already know this. But usually if you're doing an epoxy or some kind of a resin, you have two components that are usually mixed together. They come separate and you have to mix them. And then that sets off a chemical reaction. Often it's an SN2 style reaction. And basically that means that these epoxides start off with some kind of catalyst and then they keep reacting with each other that form a long polymer chain. And that either makes a glue like an adhesive or maybe a resin if you were pouring it, on top of a table or something. So that's where you may have already encountered epoxides or Williamson ether synthesis in your everyday life. See, chemistry is good for things sometimes. All right. One last reaction type to discuss, and then we'll call it for the day. So this last reaction set is called oxidation reactions. And you may be already having some PTSD style flashbacks of redox reactions and oil rig from Gen Chem. And I'm here to tell you that this is not quite the same. These are organic oxidation states and they're very different from Gen Chem. So I promise you, you will love these way more. You will not have to go back to that good old Gen Chem oil rig or whatever mnemonics you use to remember oxidation and reduction. So when we talk about oxidation in organic chemistry, we like to talk about these oxidation states. And we have basically 5 different states that we can be in. We have from 0 to 4 different oxidation states. And there's no math required here, except for some rudimentary counting, which, as I think I said really early in the semester, I am not even always that good at counting. So if that applies to you, check yourself a little bit, but I promise it's easy counting. We have oxidation states 1, 2, 3, and 4. You also see 0, but 0 is kind of boring. We don't see it that much. And 4 you also won't see very often. So what are some examples of these oxidation states? And how can you tell what's oxidized versus not oxidized? Well, there's kind of a hint in the name of oxidation states. We're looking for oxygen. So if we have a lot of oxygen, we're highly oxidized. If we don't, we're not very oxidized. So what's an easy way to make an organic molecule that has no oxygen in it? Well, we just need a carbon. And if we don't put any oxygens there, then it'll want to have some hydrogens. So we'll get CH4 or methane gas that has no oxygens on it. So it's not oxidized at all. Then if we go up a little bit and add some more oxygen, we can have some kind of carbon group. I'm just going to abbreviate that with R. And if it has one bond oxygen on it, that oxygen will also want to have a hydrogen. So we get to basically an alcohol. That is in the first oxidation state. The second oxidation state just needs to have sort of more oxygen to it. So there's a couple different ways that you can do that. The most common way that you'll see is if you have some kind of an R group with a double bond to oxygen. right? So that's technically the same number of oxygen atoms, but it's more bonds to oxygen. And so maybe there's still one hydrogen there. So more bonds to oxygen means more oxidized. And again, to keep going in this pattern, if we go up to a carboxylic acid, now we've added another oxygen that's in the 3 oxidation state or third oxidation state. And the only way to get more oxidized than this is to go all the way to CO2, which has 4 different bonds to oxygen. So again, our kind of lowest oxidation state of 0 and our highest oxidation state of 4 they exist, but they're not going to be common, so you don't really need to worry about them. But 1, 2, and 3 are highly common, and they're definitely going to be a part of this unit. So when we were talking about alcohols in the beginning of this video, those are all in this first oxidation state. And now we're going to talk about oxidizing them further. So when we think about that, when we're doing oxidation reactions, we want to think about increasing the oxidation state of a particular carbon. And we basically do that by just increasing the number of bonds to oxygen. So you hopefully can see that in this trend already, that we have a 1 bond to oxygen compound here, and we have 1, 2 bonds in that pi bond there, and then we have 1, 2, and 3 in our carboxylic acid. So that's where those numbers come from. That's the sort of oxidation states that organic chemists like to work in. So how do we feel about that? No math involved, you just need to be able to count. Pretty easy, right? So with those oxidation states in mind, then we think about these oxidation reactions. So again, these are just oxidation reactions. And the product of these will be a little bit different depending on what you're given. So to start with, this very first one where we use NaOCl, that's sodium hypochlorite, which maybe doesn't ring a bell to you, but this is another big everyday life thing that y'all probably have around, or at least your parents do. It's bleach. That's literally all it is. It's a bleach solution. If you expose an alcohol to that bleach solution, what you do is you increase it in oxidation state by 1. So we're basically looking at the number of bonds to oxygen. The other way you can think about it is the number of bonds to hydrogen at that position. So we start off with this primary alcohol. It has 2 bonds to hydrogen. And then when we oxidize it once, it loses one of those bonds to hydrogen and gains another bond to oxygen. So this has gone from the first oxidation state to the second oxidation state. So that has nothing to do with this number, right? It has everything to do with the number of bonds to that oxygen. So this NaOCl is what we would call a little bit of a weak oxidant, meaning that the bleach itself is the oxidant. It is the thing that is doing the oxidizing. Don't worry about that nomenclature. I'm not going to test you on that. But it's weak in that there's still this hydrogen there. That didn't get oxidized away. It's still sitting there. It's only gone up 1 oxidation state. So this is a little bit different from our next example, where we're going to take the same alcohol, a primary alcohol with 2 bonds to hydrogen there at that same carbon. If we use this stuff, CrO3, which is chromate, in the presence of sulfuric acid and water, this is going to do a much stronger oxidation, meaning that it's going to take away all of these hydrogens that it possibly can and replace them with bonds to oxygen, right? So now you can see we not only have a double bond to that oxygen, but it took off this last one, right? And it replaced that H bond with this OH bond. So because it's a stronger oxidant, it just goes more high up our oxidation state scale. It removed all of those possible protons at that alpha position and turned them into bonds to oxygen. So then that might seem like it's a little bit weird when we look at this last one, right? Where we take that same reagent, our same strong oxidant, but we only go up 1 oxidation state here, right? Because this is in the number 1 oxidation state. This compound is only in the 2 oxidation state. Why is that? It has to do with the number of hydrogens here, right? There is only 1. Right? Since that is a secondary alcohol, there's only 1 hydrogen, so it can only go up 1 oxidation state. Anytime we're adding these bonds to oxygen, we have to be removing bonds to hydrogen. So if there's no more hydrogens to remove, we kind of stop and we get to this functional group here where we have that pi bond to oxygen. So these are some kind of goofy reactions as far as the mechanism is considered. You will not be asked to draw the mechanism for these. In fact, I'm not even going to show it to you. If you're curious, you can look it up on your own time, but I think you probably got some better things to do instead. So what I'll leave you with after the end of these oxidation reactions is a little bit of an application or a PSA for you about oxidation reactions and alcohols in general. This is the alcohols unit. And so I'd like to take this moment to say, whatever you're going to do with alcohol in your own time, fine by me, but do not drink and drive. It is a stupid idea and it will hurt you and it will probably hurt others. So do not do it. Get a taxi, call a friend, call your parents, anything, don't drink and drive. And the reason you don't want to drink and drive is because if you get pulled over by the cops, they're going to make you do chemistry. That's right. A breathalyzer test is simply an oxidation reaction. Breathalyzer utilizes a compact version of a chemical reaction to give a readable value of how much alcohol is in your system. You basically exhale into the breathalyzer. There are some alcohol vapors that are going to come off on your breath. It has this mixture of this sort of chromate salt in there. And when this reaction occurs, you're going to be changing the oxidation state of the chromium. Don't worry about that. But what it means is that that sort of colorful chromium salt is going to change its color. And then using that color change in spectroscopy, they can do some math to turn that into the numbers that you would hear quoted to you. But hopefully you won't hear them quoted to you or your friends or anyone else because you're just going to do the responsible thing and not drink and drive. All right, with that PSA over, I want to give a quick overview of what we talked about today. We have a couple of reactions that form alcohols, and these are the ones that we sort of already knew, right? We did the hydration of alkenes, that was in chapter 6. And then we did the SN2 reaction with NaOH, that was in chapter 8. And now we're learning some new stuff about what we can do with those alcohols, even though some of them are based on mechanisms that we already learned last unit. So we have the dehydration of alcohol to form an alkene. We did a halide substitution of an alcohol to make either chlorides or bromides. We did the Williamson ether synthesis, which maybe is a little self-explanatory that we made ethers out of that. And we did oxidation reactions that can give you various products, depending on which oxidant you use and what your starting material looks like. So there's 4 new reactions to kind of add to our chemical reaction library and a couple, reviews of some stuff from last unit. And so with that, there's definitely plenty of stuff to review. You should know the mechanisms for all of these reactions except for the oxidations, of course, which we didn't even show you, so don't worry about those. Those are more, you just need to know those in a PTP kind of style of question. Make sure you're feeling comfortable with doing those carbocation rearrangements in any case where you're doing an SN1 or E1 type mechanism, and that you're feeling comfortable with practicing predicting these products, right? So analyzing reactant that you're given, analyzing what's above and below the arrow to get an idea for what's going to react with what, and then that will help you predict the product. If this is all feeling pretty comfortable, you can look forward to something a little bit different where we're going to learn about all the magic of benzene and a concept that we call aromaticity. So if you have any questions about alcohol reactions, either forming them or transforming them into something else, feel free to leave a comment here, post in the discussion forum, stop by office hours, or send me an email. Until then, take care.